In this lesson we'll practice converting binary numbers to hexadecimal numbers, and this might be useful if your programming language requires that you enter in values in hexadecimal instead of decimal. Like for instance, in this particular color here, color 1 that I'm using, it has a value of 255 for red and 128 for green and 0 for blue, and I'm able to enter in the colors in decimal format in this particular program, but not all programs allow that, and sometimes you're required to use hexadecimal, or you just might want to use hexadecimal instead. So here I have the equivalent binary value for the first two numbers here. Here's 255 in decimal, which is the binary number 11111111, and that just equates to each one of these bits being turned on, if you recall from the lesson on binary numbers. So here's the ones place and the twos place and the fours place, similar to how you would have in decimal, the ones, the tens, the hundreds, and the thousands. But in binary it's a factor of 2. 1, 2, 4, 8, 16, 32, 64, 128. So for this particular binary number 11111111, that place, the 128's place is turned on, the 64's place is turned on, the 32's place is turned on. They're all turned on, so you would just add each one of these numbers together. 128 plus 64 is 192, plus 32 is 224, plus 16 is 240, plus 8 is 248, plus 4 is 252, plus 2 is 254, plus 1 is equal to 255, them all being turned on. And in this case, here's the binary number 128. The 128th bit is turned on, but all the others are turned off. And in this last case, here's a number 18 in decimal. So there'd be the 1, 2, 3, the fourth location, 1, 2, 3. So this 16th place is turned on, and the 2's place is turned on. And that's how you get the number 18. But now what if you want to convert these into a hexadecimal number? So really what it is, since hexadecimal really just runs from, hexadecimal numbers are just, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, and F for the digits 0 through 15. So there's only the numbers 0 through 15, but yet we want to be able to represent a number as high as 255. We want to represent the range 0 to 255. So what we do is we essentially break these up into two individual 4-bit numbers. And you only need a 4-bit number to represent the values 0 through 15. And you can verify that if you were to take, say, these 4 lower bits like this, and you add 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So it only requires 4 bits to make up the numbers 0 through 15. And so that's what we want to do, to create two individual hex digits to represent the entire binary number when you actually put them all together. So in this case we have, let's look at this first one here. So it'd be 1111, meaning that they're all turned on for this particular location. So the 8th bit is turned on, the 4 is turned on, the 2 is turned on, and the 1 is turned on. So that particular number would be the number 15 in hexadecimal. Well, 15 in hexadecimal is equal to F, like that. So we would give that, the first one I'll say is equal to, the first digit is an F, and then the second digit, the second set of 4-bit binary number, which is a nibble we call, and that would also be an F. So it'd be FF in hexadecimal. So it's really just two individual hexadecimal numbers like that. And so let me see what this is. So here's, now let's take a look at 1000. Well, again, we're just having to look at a 4-bit number, so that means the 8th place is turned on and the others are turned off, like that. So that would be equal to 8. So that digit is 8, like that for the first one. And the second one, well, they're all turned off, so that's just 0. So it would be 80 in hexadecimal. And then for the last one, we have 0001. Well, that'd be the 8 is off, the 4 is off, the 2 is off, and the 1 is on. So that's just the hexadecimal value 1, and in this case we have the 8 is off, the 4 is off, but the 2 is on, and the 1 is off, so it'd be 1 2 in hexadecimal. And actually we call these binary coded decimal when you have a couple of hexadecimal digits adjacent to each other like that. But really what it just turns out to be is it's just two individual hex digits right next to each other, and then when you combine them together and look at them as a solid number, then that's how it becomes a complete 8-bit number or a single byte. So 255 in decimal is equal to FF for hexadecimal digits, and 128 is 80, and 18 is equal to 12. Okay, well that's it for this lesson, and I'll see you in the next lesson.